So one point to consider in yesterday's lecture, right? We found that short channel effects predominate when you compare VGS minus VT over L and EC. Okay, so that could happen for a transistor of any length on any process. So some of you had a couple of questions about it yesterday after class. So the way you would define short channel is, if you even for let's say a large, you don't have to consider a deep submicron process. You can go for let's say a 0.5 or 0.75 process, and what you would see is, if you apply a large enough overdrive, your VGS minus VT over L will become large and comparable to EC, which means you would see a predominance of short channel effects. Okay, so it just so happens that as the process scales and your length gets smaller and smaller, your VGS minus VT over L gets larger and larger. So for smaller and smaller overdrives, for smaller and smaller VGS minus VT, you get into the short channel domain. That is the only difference. Okay. And somebody else had a question about the fractal capacitors few days back, I think. So I have put up the paper, the fractal capacitor paper. You can take a look at it. It has a sample figure. Okay, it has an example of how you would, for a given area, how you would increase your perimeter. Okay. Okay, so just to give an idea of what we are going to cover over the next few classes. So I was thinking about whether to include today's lecture at this point of time in the course. What we'll do is we'll do what is called frequency planning. Okay, so we'll look at how you would choose particular frequencies in your receiver. We could have done this later. So there is remember when we talked before, there is the RF system architecture portion and the circuits portion. So even though this course concentrates a lot on the circuits, we also wanted to cover a little bit of systems. Okay, so what I'll do is I'll cover a little bit of the systems portion today. Then because we need to move on to next few classes, linearity, noise, and we'll see that naturally leads on to your LNAs and then mixers and so on. So before we study the circuits, we need to know where these circuits are used, right? So that's why I wanted to give you a sample receiver. We'll look at how you do frequency planning. We'll go ahead and study linearity, why the linearity we study will be different from your normal analog linearity, analog measure of linearity. And then we'll look at noise, then we'll look at LNAs, mixers, oscillators and so on. Towards the end of the course, we'll come back to architectures and see what kind of different architectures are available, and we'll try to cover more for transmitters and receivers. Okay, is that fair? The main reason it's actually organized this way is because if you do the systems portion first, you'll come up with the circuits portion towards the later part of the course, and at that time you won't have enough time to finish up your projects. So because your projects are going to be LNAs, mixers and VCOs, designing these circuits, right? If we reach them too late in the course, a few more lectures ahead, your project timelines will get too compressed. That's why I'm covering the architectures portion towards the end of the class. Okay? Okay. Okay, so we'll call this introduction to RF systems. So not a good way to start off class. Okay, so if you look at a typical received RF signal, right? So let's say you're interested in some particular band of frequencies. What you'll see is there are different people transmitting at different frequencies. So you'll see a bunch of other things around you which could be much higher. Remember we talked about, let's say if you take your mobile cell phone, you're receiving something which is a few kilometers away, whereas there could be a person transmitting something very nearby in a totally different band. So nowadays your RF bands are very crowded. Okay, so you could see a case like this, and so you want to receive something like this. So your typical receiver would look like this. You have your antenna, and then first you want a band pass filter. Okay, because you want to get rid of junk outside your band. Then you'd have your what is called your LNA, a low noise amplifier. Why do you need a low noise amplifier? Why wouldn't just any amplifier do? Right, noise figure. It's going to affect. What's going to happen is you want to add as little noise as possible right at the front, because you don't want to corrupt the signal up ahead. Okay, and the signal you receive is probably, if depending on where the transmitter is located, it could be in maybe microvolts. Okay, so you want to bring the signal to an appreciable size, amplitude, before you process it further. And then what you do what is called a mixing operation. We'll see what this is. So the other input to the mixer comes from a VCO, which is in some kind of feedback loop. Okay, so it's controlled, so it's a voltage controlled oscillator. It is controlled by some control voltage. It's usually in a feedback loop inside a phase lock loop, and that is the other input to the mixer. And the output of this, for now we'll see. So the output can be processed further. Let's consider just this portion now. So we saw that you need a baseband, you need a band pass filter to clear out the other stuff, right? Now if you look at the kind of selectivity you might need to give you some certain numbers. So let's say this is your desired signal. Okay, so this, let's say it's at 900 megahertz. Your actual bandwidth of the signal could be very small at this frequency, and your surrounding interferers could be very high. So let's say your next interferer could be just 45 kilohertz away, and you could have a case where it's something like 60 dB higher. So if you see the kind of, so let's say if you were to use a simple LC filter, right, or something similar to just get rid of these interferers at this offset and at this frequency, your effective Q is probably going to be somewhere around 10 power 7. Okay, so that is the reason why. So that is a typical kind of selectivity you would need. It's tens of thousands, equivalent Q of tens of thousands. Okay, and inside this you also have to distinguish between, so this portion is the band, right, and remember each one of these bands is split up further into channels, right? We discussed this I think in the first class. Okay, so this first, the way this is usually split up in most systems, you would first receive the whole band, because you don't want to do a lot of processing up front. So you just received all bands, so you receive the received signal of all users, and then you would select the channel from that, from inside that. So you do it in multiple stages. Okay, so let's look at what is called the single conversion super heterodyne receiver. Okay, you'll see why this is called single conversion. Later in the course we'll study the double conversion receiver. Okay, and heterodyne simply means it uses a mixing of frequencies. Heterodyne just means a difference of frequencies. Okay, and of course it's called a super heterodyne because Armstrong was able to use this to actually transmit and receive at much higher frequencies than what it was originally proposed for. Okay, so the person who invented this is called Armstrong, Edwin Armstrong, in 1917 or 18. So you have the band select filter. You have the LNA. And this is quite often called your LO or local oscillator. And you have some kind of control, right? And so this is your desired RF frequency. And this is called your LO frequency. And the output is called IF or intermediate frequency. Okay, even though IF stands for intermediate frequency, you will quite often see people calling it IF frequency, which is still okay. Okay, now in common parlance, that's perfectly fine. And then you have an IF amplifier. And actually, let me make a small error. So you have what is called the IF filter followed by an IF amplifier. And then you have a bunch of DMOD circuitry. Okay, so we saw that the band select filter, you want to select out the band of interest, and your LNA, it's going to offer some amount of amplification with very little noise. What does the mixer do? So your basic mixer operation is so let's say you have two signals. So let's say this is your RF signal, A cos omega RFT. So your mixer is simply a multiplier in the time domain. So you can rewrite this as right. So if you product of two, what is cos A cos B? Half of cos of A plus B plus cos of A minus B. Is that clear? So what does it mean? So if you multiply two cosines in the time domain, you multiply two signals in the time domain, you get what is called frequency translation. Okay. So so that is what the mixer does. So let's first of all assume omega LO is greater than omega RF. This is not necessarily true, and you can actually choose to have omega LO less than omega RF, and that will still work fine. Okay, so this is called high side injection. Okay, if omega LO was less than omega RF, would be low side injection. Okay, so for now we'll go on with assuming omega LO is greater than omega RF. Okay, so what does it look like in the frequency domain? So let's say your desired signal looks like this. Okay, let's draw it a little bit better. And it has an amplitude of B, right? What did we assume? Let's go back again. We assumed A for the RF and B for the LO. And in the frequency domain, you convolve it with the sinusoid. So you have the cosine is two impulse functions, right, at plus or minus omega LO, and of height B. So at the mixer output, what do you get? So you get okay. So what is this? Remember, we call the intermediate frequency as omega LO minus omega RF, right? And it minus omega IF. And what do you get? You also get the second harmonic, right? Rather, the sum of the frequencies, not the second harmonic. Okay, so for low IF design, you would want a very, for an easy IF design, you want a very low omega IF, right? Choose a low omega IF. Okay, so now let us look at, you do have one issue with this. What is called the image problem. Okay. So we looked at omega, let's consider just the positive frequencies. So you have omega RF and omega LO, right? Higher. Okay, so let's look at what will happen for a signal which is on the other side of omega LO. Okay. So let's consider, yes. Because you're going to actually we'll look at it after class, because it's pretty straightforward. Yeah.
Reflect the boss and take the convolution. Like this, like I don't get any signature change. Convolution, either one can be reflected.
Yeah, you can do that. No, but there should be actually. There will be a signature change. Let me look at it and tell you. Okay. Let me look at it and tell you guys. Okay, so omega RF, and so let's look at a signal which is omega IM, which is omega LO plus omega IF. Okay, so what happens? So you're actually convolving it again, right? So if you actually look at the result at the output of your mixer, so this is your omega IF, and you're going to get something at omega LO plus omega RF. And you're going to get your omega IM on top of this. Yeah, what about this? Omega IF. This is omega IF. Yeah, so remember this is omega IF, right? Right? And you consider a signal which is omega IF on the other side. Right? Okay, and what does that give you? So now what that means is, in reality I have shown it much smaller, but it's going to fall on top of your signal. Whatever is there is going to fall on top of your signal. Okay, so let's look at the mathematics. So let's say that some other amplitude C cos omega IMT, and so again you're going to get BC over 2 right. And of course, one of the reasons you're getting this is because cos of omega Im minus omega LO is the same as cos of omega LO minus omega Im, right? That's the reason why you're getting this problem. So that is called the image. So what is your image frequency? So right, omega LO plus omega IF, or you can also write it as, sorry, did somebody say something? Yes. So right, that is also true. You can write it like that, and you can also write it as, so it turns out you have one more equation, right? So there are a number of ways of representing this. Okay, and the other thing to remember, of course, is omega IF, omega Im minus omega RF is to omega IF. Okay, so just remember, I mean, these frequencies. Okay, so how would you solve this image problem? So one way to do it is to, so let's say you have image, so you can add a filter, something like this, okay, on your RF side. So this is called an image reject filter. Okay, so now let's say you want to design your image reject filter. What kind of IF would be suitable? You want to have a large IF, right? So if you want to have make your image reject filter design easy, so the farther these two are apart, the easier this filter design is going to be. Okay, and you need an image reject filter in all cases. Okay. So what you'll see is, based on this, this is a fundamental trade-off in your signal conversion design, receiver design. So based on this, you see a bunch of different architectures. So you have what are called direct conversion receivers, and you have what are called double conversion super heterodyne receivers. We'll look at both of these towards the end of the class. Okay, I mean, actually not towards the end of the class, later in the course. Okay, so let's do a sample frequency plan, right? So what this means is, so we need to do some kind of special frequency planning, right? So you need to be very careful with the frequencies you choose. So let's do a sample frequency plan. So let's take the case of AM radio. Okay. So the AM band happens to be 530 kilohertz to 1610 kilohertz. And it has 109 channels between these, and channel spacing is 10 kilohertz. Okay. So you have a bunch of channels, right? So you have 530 and so on till 1610. So next we need to choose the IF. Okay, so you know what the frequencies are and what signal you need, what the band is. Next, choose IF. Okay, next step. So what is the standard? If you look at the standard IF chosen for FM is 455 kilohertz. Okay, so let's choose that and see what happens. Okay, and we'll also assume, let's assume we want to tune to the first channel. So let's say we want to tune to, this is the standard IF chosen, and let's say we want to tune to 530 kilohertz. Okay, so now what that means is, so your FRF is here and that's 530. Okay, what is your FLO? Right, 985 kilohertz. What is your image? What is your image frequency? 455 times 2 is what? 910. So it's 910 plus 530, right? 1640. Sorry, 1440. Right? Okay, and your FIF is going to be here. Note that, okay, we'll look at two things. So let's say you receive your FIF, right? Is 455. Now one thing you should remember, your 1440, it so happens, is a valid channel. So somebody else is probably transmitting on top of it. So you are definitely going to get something here. Okay. Now what is the second thing you notice? So if you're going to choose FIF is 455 kilohertz. If you want to tune to a different channel, you need a different LO. Okay. So your FLO is going to track your FRF. Okay. So if you want 540 channel, you're going to have to move to 995 and so on. Okay. So let's say you want to tune to 700 kilohertz. Okay. So your FLO is 1155 kilohertz. So this is your RF, this is your LO, and is 1610. This is your IM. Okay. So what does that mean? So what is 1610? it so happens that 1610 is the last channel. Okay, so what that means is, so it so turns out that if you choose an, okay, so this is 455, right? So if you choose any, for this particular channel, if you choose any IF larger than 455, your image is going to fall out of band. Is that clear? Okay, so now that means so what does it mean when you try to move your image out of band? Remember that in any receiver you have a band select filter, right? So if you end up moving your image out of band, your image is already knocked down by your band select filter a lot, okay, which means you don't have to worry about your image anymore. So let's try to choose, so an FIF appropriately, right? So what should FIF be? We need to choose greater than by 2, right, which is okay. Is that clear to everyone? Okay, so let's say we choose, so let's say we choose 545. Of course, the larger you choose, the easier it is, the more it will be knocked down by the band select filter. But of course, you also have to worry about the IF amplifier design. So let's just choose just enough, just outside the band, because we are going to assume that your band select filter is a really good filter. Because yeah, you might have an option of using an off chip filter, for example. Okay. So what happens? So let's say again, let's look at your 530 kilohertz. What is your FLO now? 545 plus 530, is it? So 1075, right? And your image is now 1075 plus 545. So it's 1620 kilohertz. Okay. So what that means is, okay, so we know that. So let's start using some colors. So your last, so this is your band select filter. Okay, you assume it's going to knock down things outside. Okay, and of course the in-band things are still going to be there. So this is 1610. This is your last channel, right? So let's see what happens when you do the mixing operation. So at FIF equals 545, so you're going to get your desired signal. And what you're going to get is, from 1620 you're going to get something, but it's going to be much smaller. Okay, that is your image. And at 535 kilohertz you're going to get your 1610, right? Your channel at 1610 is going to come to 535, but you're going to end up putting a filter on top of this. Let's use a different color. Okay, that is your IF filter. So your final system is going to look like this. So you have this It's triggering me. Okay. So you have a band select filter. You can have an LNA. So in this case, you can have some extra image reject filtering if your band select filter does not remove it completely. It's optional, okay? You have your mixer. And so on. This is your IF amp. Okay? So this is a fixed filter. Okay? So we'll come back to we'll conclude filters with this, right? Sorry, we'll conclude RX architectures with this for now. So what we'll do is we'll see how we are going to design LNAs, mixers, and we'll go to VCOs, and after that we'll come back to RX architectures, the double conversion. Then we'll look at your power amplifiers if we have time, maybe some simple architectures. We won't get into any detail, and then we'll go with that. Okay. Now there is some more stuff, but I think I'll stop for today because there is really not a lot of, it's just a lot of math. Okay, just how to represent signals. So we'll stop with that for today. Okay. So tomorrow we'll start off with linearity. Okay. So we'll look at, first of all, we'll look at things like linearity, time variance, time invariance, what all of these mean. Okay, and which blocks will be linear, which blocks will be time invariant, time variant, and so on. And then beyond that, we'll move on to what are the measures of linearity in RF systems and why we need different measures of linearity. And then we'll move on to noise, followed by we'll have two-port noise theory, and we'll see how you apply two-port noise theory to LNAs. So from there so this is kind of the rest of the course. So we'll look at, so that is when you get into the meat of the course, right? So we'll see how you design LNAs, what are the different architectures. Then we'll look at what are the different architectures of mixers, and oscillators. We'll probably have a few classes. I don't know if we'll be able to do justice because it's a pretty big, pretty large topic, because you have phase noise and oscillators and so on. And only then. So it'll be a long time before you see receivers again. If you want, you can actually take a look at the text, either the RF microelectronics textbook by Razavi or the CMOS RF IC design by Thomas Lee. Both of those do a decent job. I think the Razavi book does a little bit of a better job. You can take a look at it if you want to learn a little bit more earlier. Okay? Okay, so we'll see you tomorrow morning.